We are on path integration part 6. Let's talk about last time. So we are on path integration part 6. All right. Now, last week we got to a kind of like a, I don't want to say a final form, but we got to this pretty complicated form that's almost to our final form of this functional integral, okay? And it wasn't equal, it was proportional because we had some constants we had to deal with, right? And the proportionality was something like this, okay? So we have the sum from of v, from 0 to infinity of 1 over v factorial. And don't get worried about this, guys. If this looks too much for you, then just look away. No, I'll kind of explain again what we did last week and where this came from. 1 over I, the functional derivative of j of x, right there, cubed, all to the power of v times the sum of p equals 0 to infinity, 1 over p factorial. And I'll just give you I'll give you the little rundown of what all this stuff is. And if you've been following along, you maybe know what all this stuff is. J of y, our propagator, we love our propagator. Wow, turns into a propagator, you get the picture. Z all to the p. Now, this is the stuff, this is the sums that we got last time. Oh, let me turn my my arm chat on. Arm chat. It's like armchair, except it's... Now, this is what we got on last Friday when we did part 5.
I understand nothing. Good day, sir.
And we had started with this functional integral. It's supposed to give us some sort of representation of if we have two states, both in the ground state, and that is to say a state without a particle, right? And we want to figure out how many different ways we could go, or paths, if you are willing to accept the paths in what we call Fock space, then how many different ways, how many different paths could you go from the ground state to the ground state? And we figured out that we could take this amplitude and simplify it, or just change it and modify it all the way until we get to this proportion, where these are going to be full sums. So like, think about this as being like, if v equals 0, then you put 0 in for the v's, and then you'll have 1 plus put 1 in for v, and then you'll have another 1, and then you keep going, right? And that's just a sum of all of those things lined up. Whereas here, you put a 0 in for p, and you do the summation like that. And then every time, and these are multiplied together, so every time you go from one term to the other, it's kind of that same thing we did with Java's question, right? Where we had some factorials like this, except now instead of something like with just 2 factors, we have infinity amount of factors, and we're multiplying them together, but the FOIL stuff still remains the same. Like, we still multiply all these pieces together, just like in Java's question, okay? Except now, like I said, we have infinitely large factors. Now, each term that you multiplied together became one probability of a path, like of a specific path to get to the 0 state to the 0 state. Okay, and we figured out that we can use these v's and p's as our, and we had this E equals, if you guys remember, E equals 2p minus 3v, and what did that tell us? That told us that these e's were external sources, or external legs of the graphs. These p's were the propagators, and these v's were the vertices of the graphs. And using what we know about this, we can then say, okay, well now we can construct, for any given v and p that get multiplied together, we can construct the appropriate Feynman diagram. And we set out rules so that we could do all of that. So then we can go ahead and we can set up these diagrams with appropriate, like I said, with appropriate vertices and appropriate propagators. Okay, so that was what we did last week. And we saw these things, and we did that. And we also saw that for any 3v vertices, so there's going to be 3v for every vertex, vertices, how do I spell it? Where is it? I don't know. Vertices. I don't know. Someone correct me. How do you spell vertices? And they act on any, 2p sources. Then we can express that as saying that there are 2 p factorial divided by 2p minus 3 v factorial, and this is just a permutation. Like we said, this is a permutation. And this many combinations, don't get confused by the language. I'm saying there's this many combinations of p's and v's, or of diagrams, excuse me. But some are identical. That should be kind of obvious to those of you who have taken like probability and random variables, that like regardless of how many permutations we do, we're going to get a bunch of identical graphs, okay? I see, Admiral, thank you for that, I appreciate that. And now I know what another term is too. Now, I will also stop to just say for a second that the notes are available from, I take all of my own notes and I post them to Discord prior to the discussion. So again, !Discord, and you can go into the Discord to gather my notes. So that way you don't have to write your own. You can just look on with me as I go through this. All right, so now we know that for all of there's this many identical combinations, there's this many combinations, some of which are identical. So now it's our job to make sure that we're not double counting, because we want to make sure that even though we have identical graphs, that we account for the fact that there are identical graphs. So let's leave up this big boy for a second. Do I want to leave up the big boy for a second? No, I don't think so. We're gonna go and move into take a look at some diagrams, okay? Also, there is the link to Shrednicky's PDF that he put on his website is in Discord as well. Shrednicky was nice enough to release a rough draft of his QFT texts on his website, and you can go right into on the Discord. It's pinned, so you can just go to the pins in the Discord section under path integration, and you'll find Shrednicky's QFT. Inside of it, he lays out a bunch of very interesting Feynman diagrams for this particular problem that we're doing. And you can go ahead and take a look at some of those, and I'm going to make some rough copies of what those look like, okay? But we have to get control over what identical factors are, because we know there's a bunch of identical factors. So there's going to be 4 rules that we have to follow, okay? So if you remember, there was like, if we wanted to do a tree level diagram, we had, 2 external sources coming in and 1 external source coming out. This for a phi cube theory is pretty much like the basic tree diagram. There was no, well, let's not do a dot in the center because he doesn't have a dot in the center. They come down and they meet at a certain spot. Yeah, there we go. And this was the vertex, and these were the external sources. So there's going to be 3 external sources for 1 vertex. So there's 1 vertex, so it was 2p, what was it, 2p minus 3v? Was that what it was? Oh, it's in my notes, you doofus. Yep, and then so we had 1 vertex, no propagators, so the sources was going to be 3, right? Makes perfect sense. Okay. Now, this was a tree level diagram, blah, blah, blah. So let's start talking about how to count it. So if you go back to that big equation that I had, remember that I had that one term that looked like 1 over I, functional derivative of j of x, and that was cubed. That means that there's going to be 3 ways that we can take that functional derivative of the whatever it is there, the sources. There we go. And every time we rearrange this, we'll end up rearranging these external sources. So for instance, if we have 1, 2, 3 for our external sources, every time we rearrange this, we'll have a different arrangement. So that's one thing we have to start counting. That's the first thing. So we'll have arrangement. Let's do rearrangement. Rearrangement, okay? And then we'll have a couple different ones. So firstly, let's start with the functional derivatives. Functional derivatives. So the point is if we rearrange these sources, then we're gonna have something that looks symmetrically the same. And we wanna make sure that we're accounting for that. So let's do the following. Let's count the rearrangements, and we'll call that a, what do we call that? Symmetry factor? I think it's symmetry factor. Why do I, yeah, symmetry factor. Okay, and this is gonna be, in order for the functional derivatives, because there's this term inside of that functional integral, we're gonna have 3 factorial ways of counting that. How? Well, let's consider this tree diagram, okay? The tree diagram, let's write down all the different ways that we can rearrange these functional derivatives and get the external sources, okay? So let's see, and once I do this, you'll be like, oh, okay. So we'll have 1, 2, 3, that's the one we have up there. What's a different way? Well, how about 1, 3, and 2? Oops, I done made a goof. 1, 3, and 2, so these will come down and go over. How about 2, 1, 3, you get the picture. We're gonna do 6 of these. 2, 3, 1, and these are all because these are symmetrically the same. Like look at the picture doesn't change, right? It's just moving around the sources, that's what's changing it. And then 3, 2, 1, and then 3, 1, 2. So these, while they look the same, the sources are different, so we're gonna end up double or over counting them. Okay, and I'll explain. We're gonna end up counting them too many times. Okay. That's a little bit jumping ahead, but that's the functional derivatives. So for the functional derivatives, we have a 3 factorial, okay? So let's get rid of this now. And then you guys, I'm not gonna just keep having these all over the place, so you'll see that this is the same thing as right there. Okay, so now what's another one? Well, how about vertices, right? So vertices. Vertices, we're gonna have a factor of v factorial. Well, how's that gonna work? Well, think about the other tree diagram that we talked about where we had sources out here, okay? Let's label these vertices 1 and 2. Not 1 and 1, that doesn't make sense. What happens if we take these and swap them? Take these vertices and swap them, but leave everything else the same. So we'll have, 1 prime, 2 prime, 3 prime, 2 prime, or yeah, 2, well, let's do 2 double prime, there we go. 1 double prime, and then 3 double prime. Okay, so now all the primes are different than these vertices. These vertices are just 1 and 2, but we can swap them and imagine that nothing else changes, right? There's gonna be, let's see, 1 double prime, 3 double prime, 2 double prime. Now we put 1 here, we'll put 2 here, but this vertex, or this external source is still 2 prime, and then 3 prime, and then 1 prime. Actually, in reality, these should all be single prime too anyways, but nevertheless, let's not worry about that. But anyways, we have to count, we have to make sure we're counting, right? So then vertices, you get the point. Like these are all just rearranging things so that we can make sure that we're counting for everything. So the symmetry factors are important. Obviously, if we want to have appropriate numbers, let's rewrite this too. If we want to have appropriate numbers for our amplitudes, and we want to make sure that we're not counting too many graphs or too few graphs. So here we have functional derivatives, then we have vertices, and that's v factorial, and then we have propagators. I always find the combinatoric stuff to be the most enjoyable. But let's talk about propagators flipped first. And that's going to be the same thing, except now, think about as the last one, except now instead of just flipping the vertices, what if we actually take so the vertices are a thing, right? We labeled the vertice 1 and 2, and then we changed the vertices from 1, from 1 to 2 to 2 to 1. Now what if we take the propagator and literally flip it around backwards? So now we could have some propagator with some momentum p, and we'll say it's going this way. Well, then we can actually take this and reverse it, so now it's p going this way, and that's going to be another graph that's going to work perfectly fine. And we have to make sure that we're not counting too little or too few of those flip-flops. So for each propagator, there's just going to be a factor of 2 factorial because that's how many there exist. We can take it and go this way, and that's about it. Okay. Okay. So next we have one more symmetry factor we have to pay close attention to, and that's the actual propagators rearranging. And for those, it's going to be very similar to the vertices. It's just going to be p factorial because there's going to be that many propagators. So suppose we have something that looks like, you know, a loop propagator here and a loop propagator there. Let's label this propagator 1, this propagator 2, and this propagator 3. Now what we can say is like, okay, well, this is fine, but this is also going to be an option. 2, 1, 3, right? So for 3 propagators, because we're going to say this is a vertex, and these are a loop propagator, and then we have a normal propagator, another loop, and then each of these vertices has 3 things going into it, so the vertex is good. Everything looks fine here, but you can just change the propagators around, and again, it looks identical, just like we changed the sources around, and it looked identical. So there's these factors. But even when we do this, so now we're counting all of the ways that we can rearrange the P's and V's so that we can account for, and the E's for that matter, so we can account for all of the things that are going to exist inside that monstrous the monstrous functional integral at the beginning, right? But there's a problem. The problem with all of this is that this is always going to end up, not always I should say, the problem with this is going to be overcounting. How is it overcounting? Well, before we were undercounting because we weren't counting nearly enough diagrams, and then we started counting all of the ones that look symmetrically the same, and then we got way too many of them. So how do we know when we're overcounting versus when we're undercounting? Well, that is something we just have to pay close attention to, and that's what we would call the excuse me, I think I got my terms mixed up. I think that's what we call the symmetry factor. Let me double check that really quickly. Yes, that is the one that we call the symmetry factor. The ones that we are overcounting are the ones that we call the symmetry factor. So the ones that we were doing before are just counting all of the terms, all of the ways to rewrite the things that are symmetrical. And then we're going to have some overcounting symmetries, and that's going to be called, and then how many we overcount is going to be called the symmetry factor. And that one, we have to be a little bit more observant to do, right? So how do we do that? Well, let's think, let's give you an example of an overcounting the symmetry, okay? Erase this stuff, da da da. And if anybody's like studied this or like has taken this course in depth before, then it's probably best to like realize that I'm going incredibly slow on this. And if anybody is not like versed in path integration, this may feel a little bit fast to you guys. So either way. Okay, so one example of overcounting is, consider this graph, right? That's a perfectly plausible graph, okay? Now what do we got here? Well, let's label the external sources. So this is going to be an external source, this is going to be an external source, and this is going to be an external source. We have 1, 2, and 3. Now let's go over here, and what do we have? Well, this is going to be 3, this is also going to be 2, and this is also going to be 1. Why? Well, because it's the same line. There's nothing happening from here. It has to be the same, okay? Now let's label the propagators. So we'll label the propagators A, B, and C. Now, what did I say? Well, there was 2 options for rearranging some of this stuff. We had one ways where we could rearrange the vertices, or I'm sorry, rearrange the sources, and another way where we could rearrange the propagators. We have 3 propagators, so that means there's 3 factorial ways of rewriting it, and there is 3 sources, so there's there's 3 factorial ways of writing each of these. Okay, but imagine, what if I just did one swap? What if I did this A propagator with the C propagator? Okay, well then it's going to look like this, where we have C, B, A, and then we can write 3, 3, 2, 2. Oh, I'm sorry. No, and 1 and 1. Sorry, this 3 should be on the inside. 3, 3, 1, and 1. There we are. So now we have, you know, all we've done is swapped these. Did I do it wrong? I did do it wrong. I did. I mixed those up. Give me just a second. 2, 1, 1, 2. Now we've done what we've done. Well, we've done a fact. We've all we did was switch the propagators, but by switching the propagators, we've also flipped the vertices. And what's going to happen when we go to flip the sources again? Like if we were to take these and flip the sources, we could get the sources like this by switching the 2's around or by switching the propagators. So there's ways of overcounting, and this is one of them. So we have to be very careful. So we can swap the vertices, which would be the same as flipping the propagators. And this would say that we would overcount by a factor of what? Well, how many ways is there to do this? Ooh, excuse me. There's 2 factorial times 3 factorial, which is equal to 12. So the symmetry factor by switching these, but for this diagram alone, is 12, just because of that, just because we can do all of that. We can reiterate the same symmetries by doing different ones of the rules that we listed before. Okay, so now we have the symmetry factor. So we have ways of counting all of the symmetries so that we can make sure that we have enough diagrams. And lo and behold, oops, we've overcounted. Okay, well, now we can kind of take care of the overcounting by dividing out by the symmetry factor. All right, so now we have all the diagrams, and we have, you know, subtracted or divided or whatever. We've gotten rid of all the diagrams that we've counted multiple times by accounting for a symmetry factor. So now there's one more way to talk about this, and that is if you are looking at Shrednicky's text, then you can see all of the different diagrams that he has listed in figures. I think it's like 9.1 to 9.11, which I'll just let you glance at the. Oh, I don't know if I can let you glance at the book. I showed it last stream, and you can look it up really quickly or join the Discord, and you can see all of the different diagrams. Well, maybe we'll take a look at it when we're done with this too. All of the ones that he lists are what he calls connected diagrams. Like you can start at one point and you can draw a line to get from one end of the diagram to the other end of the diagram, and everything is good and everybody's happy. Let me see, where do I want to start? Okay, but there's another way. There's another source of diagrams that exist inside of that functional derivatives, and that's combinations of the diagrams that he made, right? That he has in his, that are listed in figures 9.1 to 9.11. There's ways where you can add or multiply all of the diagrams together and get, or like, you know, individual diagrams together to get much more diagrams that are by default included inside that functional derivative. And what does that mean? Well, if you can multiply those diagrams together and get larger diagrams, then there's going to be symmetries that we have to count associated with those too, right? So there's just more and more symmetries that we have to account for. Montreal player, welcome to the channel. Thank you for the follow. If you have any questions, feel free to ask. Exclamation mark, ask, and your question. And or if it's about path integration, you just ask and I'll wing it. Okay, so where are we at? So there's a general diagram expression. Okay, so there's a general diagram. And that's going to be given by d is equal to 1 over sd. Now s, remember, was the symmetry factor. Sd is a little bit different. And that's going to be multiplied by the product of all of I for ci to the ni. Okay? So what is a ci? Whoops, that's a straight line. Can't make a c out of that. So ci is connected diagrams. And in this CI, we're going to include the symmetry factor, okay? So that's the symmetry factor associated with a particular diagram, right? Each one of those diagrams, we said, has some symmetries. We've added up all of the identical ones. We've divided by all of the overcounting ones. So now we have that symmetry factor, and the CI is counting for all of that, okay? Now we're talking about ways to combine all of these to make bigger diagrams. And then this is technically includes the connected diagrams by themselves as well. And then we have ni, which is the integer that counts the number of CIs. So imagine like we have one of those connected diagrams. Go back and take a look at this guy. Well, let's just say the tree one for the sake of argument. The tree is easier to imagine, right? Now we're gonna say, like, how can we multiply, you know, how many of these tree diagrams are in this higher order diagram? Well, this NI is going to account for every single one of these tree diagrams that shows up, okay? And this is part of the path integration that I'm a little bit rocky on, so again, if I make any mistakes, feel free to chime in and let me know. It would be helpful for me as well. And then this is gonna be the symmetry factor. Associated with multiple CEIs. So this is the symmetry factor that's going to count from rearranging those connected diagrams. Because like I said, now we have diagrams that are just the connected diagrams, right? But now we're also going to have diagrams that exist as multiple connected diagrams connected together. And those multiple connected diagrams are going to have ways of rearranging. Yes, so now we have this diagram is going to be a general diagram. It includes all of the connected ones, all of the combination of connected ones, and the symmetry factors associated with all of them, okay? And now we just need to kind of figure out what this symmetry factor is. Do we have a mathematical expression for it? Well, sure. I mean, there's NI factorial ways of rearranging these connected diagrams inside of themselves, right? If we want the symmetry to be the same, then if we're going to change a connected diagram, it has to be identical to the connected diagram that we're exchanging it with, right? We want the graphs to look the same. So therefore they can only be exchanged, thank you Slayer, they can only be exchanged with diagrams that look exactly like them. So this NI, this number of, the integer that counts the number of these connected diagrams as in the same one, then that's the amount, that's the factorial of that is how many we get. So we can say that SD is equal to, and then there's going to be a bunch of those different connected ones, right? Depending on the order of diagram. So we're going to say that so we're going to multiply all of the NIs together. So if there's only like 2 of one diagram, and that's it, like you're just taking 2 connected diagrams and multiplying it together, then this symmetry factor is literally only going to be a 2 factorial. Why? Well, because you only have 2 versions of a connected diagram, and that's the only diagrams you have in that entire thing. So it's just going to be a symmetry factor of 2 factorial, right? Easy peasy. All right, so are you ready for the fun part? This is the fun part for today. And we're almost done. I told you it was short. It's like a half hour. Oh, I want to leave this actually. Let's leave this. Let's get rid of this though. You guys can know that it's all of the factorials. Can I leave this too? Yeah, I think I can leave the whole thing. Why not? Let's just leave the whole thing except that one thing. So now, let's go back to our functional derivative. Functional integral, a functional integral. The one that tells us the amplitude of that specific path, or of all the paths. Now remember, each one of those combinations of factors gave you one probability for a path to be taken. Could we imagine the symmetry factor like a checksum over diagrams? Yeah, I think so. I think that's exactly what it should be. I have to double check the definition of checksum. But if I recall right, then that's the same thing. Maybe iterate what checksum is. But yeah, like I said, I'm pretty sure that's what it is. It's been a long time since I've used checksum. So this original functional derivative, we now know is going to be proportional to the sum over, this factor of countable connected diagrams of diagrams, so all of the diagrams summed up together is going to give the total amplitude. And let's kind of look at this now. Okay, what happens if we re-plug in our different things? We can say that it's proportional to, now remember, s is equal to 1 over n factorial, ni factorial. So we know that this is going to be the sum of the, and then we're going to have all the set of ni's, right? And then we'll have the product of I, and we'll substitute in our symmetry factor Ci. Oh man, I think that was supposed to be a parentheses and I just made it into a C. Oh well. And then we have that, right? Ci. So we just move this down here, okay? Maybe I can make that a little nicer. There we go. Now, ready? Take this. Flip it, rearrange this. We're gonna have the product. I. Mathematicians hate him. Ni equals 0 to infinity. 1 over Ni Ci. What does this look like? Who knows what this is? It's very important. Famous sum, the most famous sum of them all. It's the most famous sum of them all. Exponential, the red nose ring. Okay, sorry. So then let's just go up here. Z, interaction J, is proportional, not equal to proportional of Divik. Looks like scribbles on a chalkboard. It is pretty much scribbled on a chalkboard. It's the ramblings of a madman, and I am that madman. Of I, exponential, that's it, just e to the Ci, that's it. This is crazy what's happening right now, right? This is literally, and then we could just take this and we're gonna plug it in, and then if you have product of exponentials, and they're all the same exponential, then this can again be simplified even further to the integral, or I'm sorry, it's Z ij is proportional to the exponential of the sum over all Ci's. Now this is crazy, right? We have gotten rid of all of the higher order diagrams, right? We have managed to write this in a way where this interaction is now just going to be, and I don't want to say higher order diagrams, I mean all of the diagrams that are made up of the connected diagrams. The connected diagrams are still infinitely large, I think. That is something I don't know off the top of my head. But, and that's one of the prices you pay to get taught by a graduate student. But the connected diagrams is all we need right now. We don't need any more of those higher order diagrams that are connected diagrams of the connected diagrams and symmetry factors and all that other jazz. All of that is now tucked in here. And to make things even better, we need to make sure that this is normalized so that if there's no sources, that this equals 1. Right? What does that mean? That means that vacuum diagrams go away. Let's say all vacuum diagrams, that is ones without sources, go away. Just like we saw before where we had to divide out by j equals 0, remember that thing? You're using Feynman technique. Yeah, exactly. Exactly. Trying to figure out, the more I'm teaching and trying to understand things a lot more. And it's working, I think. I hope. I guess I'm probably not a good judge of that. But here we are. All vacuum diagrams go away. So is there an easier way to write this? Well, sure. Let's consider this guy right here. Now I'll say that this is j is equal to the exponential of I, this weird w thing, w, times of j, okay? Where w, or I should say iw, of j, we're gonna define as the sum of all of the connected diagrams that are not, and we'll write it like this, where you have an I not equal to the empty set. Oops, not equal, that's Ci. And what that I not equal to the empty set means is that we're omitting all of the vacuum diagrams. so that, and this ensures that, whoops, focus, okay, there we go. Sorry, it's hard to write that low. This ensures that that is true, which is what we need. We need there to be, if there's no sources, we want the Feynman diagrams to be gone. We want them to subtract away, or divide away. I think it's divide away. And then, this is all just set up for next week, okay? Next week, we go and we figure out what this means, okay? Because we're actually going to look at what happens when we apply the fields to the vacuum state, right? And so that we're going to talk about, you know, what diagrams there exist, where we have vacuum diagrams and non-vacuum diagrams and all sorts of jazz. And it's going to be interesting. I think Shrednicki does an amazing job laying this out. And this was, like I said, like this was just very much set up for next week when we hit hard. We're going to actually take a look at some states. We're also next week going to revisit those terms that I told you are the counter terms, right? The counter terms are the ones that make it so that remember, so that we could get I'm sorry, what was I saying? Oh, the base Lagrangian. We wanted the base Lagrangian. We couldn't get the base Lagrangian from the interaction Lagrangian, from the full Lagrangian, the phi cubed Lagrangian. So we introduced a bunch of counter terms so that we could make sure that that happens. Now next week, the counter terms are going to come in huge, and they're going to save us from a little bit of a predicament that this gives us. So next week, I'm going to lay out the predicament, and then I'm going to show how those counter terms get us into a good spot and make it so that, and then we'll actually solve, I think we'll solve somewhat of an amplitude. And then hopefully we'll start chapter 10 next week as well, which will be scattering amplitudes and Feynman rules. So then it's going to be some more juicy stuff, and we'll see some nice looking Feynman diagrams, some tree level stuff, and actually evaluate them a little bit. But that's not going to be, I don't know if we'll get to that next week or not. But that's what the layout looks like. This was part 6. Like I said, it was very short. It was about maybe half an hour to 45 minutes. I'll probably edit it down even lower. This will probably be the shortest one. But I wanted to get through and let you see all of the different ways that we could count the diagrams. I know many of you are going to be like, if any of you start to like look at this and you're going to say like, how do I go ahead and take, like, draw all the diagrams and then account for like rearranging them? And this is how we account for them. We have symmetry factors. We have countable things that we can do to count and then we end up overcounting, and then we gotta account for that overcounting with symmetry factors. And then we're gonna say, oh well, wait a second, we can actually make larger order diagrams. So if we, by connecting different diagrams together, and then you're gonna say, well, by connecting different diagrams together, then that makes it so that we have more symmetry factors, and then you find out that everything cancels away nicely, and it's just back to the original connection, however we want. Actually missed it. We're done for the day. We just finished. Today was a shorter day, and we started a little late too. But anyway, so that's where we're at. So next week we'll actually see the vacuum expectation, and we'll see that we get into some trouble, and then we're going to bring in back those counter terms to get us out. Hi, I'm Oculus. How are you guys? All right. Huzzah! I made it just in time. All right.